like that. There are different rules for different numerical model along with wall functions. And afterwards, we need to, after we discretize the whole domain, we can apply the boundary condition and correspondingly, and then start the calculation for the results discussion. And these are some extra stuff for the mesh sensitivity test, which we will be doing in our case. Okay, so any questions so far? Okay. Let me open up the software. Takes a while to open. Please bear with me. Oops. I selected the wrong screen sharing. Okay, there we go. So we're going to build up a model which is a flow around the cylinder. Okay, so before building up the model, we must have a how do we say, a schematic in our head, in our mind, like what kind of model we want to build. Okay, so this SolidWorks tutorial is not our um, primary scope. It's not even a secondary purpose of our class. Um, but it is necessary for us to build up a model first. So this tutorial is totally it's not that relevant to the train aerodynamic class, but it's totally for free. It is inevitable, and so and let's build up a model and give it a dimension. Say I want to have like a 10 centimeter cylinder. Okay, and so this is and then let's make it a better one. Let's give it a 800. Okay, let's give it a 2000, and let's give it a exact value. I'll say maybe 500 is enough. Okay, so that's one way to draw the model. So what about the height? Let's give it another 10 or 50 millimeter. Okay, looks about right. Okay, guys, so this is our computational domain. Okay, and let's save it as so since we're in China, a lot of softwares are translated into Chinese, but I think you guys will have to deal with it by yourself. And um, although um, it has been partially translated into Chinese, but some of the softwares, for example, ANSYS Fluent, especially ANSYS Fluent, they are not uh, either not translated into Chinese at all, or they are not fully compatible with Chinese language. By which I mean the Star CCM software. So I would prefer you guys to name the all the part names as well as the path files in English. Okay, so although you see this is Chinese, but if I'm clicking this path file, it's all in English. Some of the softwares they don't support the Chinese path. I don't remember either whether it's Star CCM or Ancestral. It's gotta be either. Okay, so that might be one of the reason. Let's say part well cooked. Okay, so by saying part well cooked, uh, we I'm going to show you a new part. This is uh this is another type of model. So let's say part how do I say medium well. So by saying the part well cooked, we have a uh, model like this. Okay, so this is a computational domain. All the grayish region, we have the gray computational domain, and um, we have drilled a hole in here. Okay, so that we have a empty cylinder. That is because all we cared about is the fluid domain. Okay, the solid domain we don't really care that much. Okay, so in real study, you can imagine this cylinder as a train and this as your computational domain. So um, in, for some of the cases, you just have a train model, right? As fluid dynamic expert, they cannot provide everything just perfect for you. So they only have the train model. So what you have instead, so what you have instead is a square in here, okay, and then you need to this 100, 500. And I want to go all the way down to the other surface and unselect the merge surface. So we have two models, one model like this and the other model like this. Okay, so these two parts are overlapped. So like I said, the SolidWorks software is not very um, robust in model processing. Uh, so that's why we usually use rhino, rhinoceros, or other or CATIA, other very complicated geometry softwares. Okay, so so let's save it. Save both of them. I will show you how to process them in Star CTM. And then after we have this file, we need to export them into a proper format. Let's try step 214. Okay, and also we need to open this file. Okay, and also let's save it in the format of step 214. Okay, and oops. Okay, and I think now we are done with the model building process. So let me open the schematics. For the ones who has the chance or opportunity, I would like you to build up this model in SolidWorks. I think this is very easy because in my demonstration it only takes me like 2 or 3 minutes, so I can give you 5 minutes to build up this model, and after 5 minutes I will proceed because it will may be very difficult for you to follow up if you don't have enough time to repeat after me. It will be a very forgettable lesson. Okay, I give you 5 minutes to build up this software, build up this model, this simple model. It can be either SolidWorks or other AutoCAD 2D, 3D model building software you want, as long as they can be exported into a stat file. Okay.
What's the thickness?
The thickness is 500, I think. Let's say, let's check the thickness. 500. There we go.
Right.
Okay, I think this is a better demonstration. So you have geometry features right in here. Okay.
Sorry, Losher, the distance between the center of the cylinder and the top surface. Losher. Wait, Losher.
Yes. Okay. I'm sorry.
Yeah,
I turned off the
sorry.
mic. It is in the center. So
Yeah,
the width is 800. So the location would be the distance would be 400.
okay, it's in the center. Okay.
Yes, it's in the center. Okay, interesting. Okay, time's up. And any questions? I have sent the files in the group chat. So um, let's uh, let's now jump to the start CCM software. Maybe uh, since I'm doing the demonstration, I may not be able to find out your uh, talkings the group chat in a very timely manner. So please interrupt me anytime, just like what Cosmo just did. Okay. So let's open up the Start CCM. My Start CCM version is 13.02 or oh 06. It doesn't matter that much. Yeah, 13.02. Okay. So you see, this is the problem. Uh, it is the Chinese. I have a Chinese operating system. I have a Chinese version software. So it just in some of the places, the language just becomes all messy. Like makes no sense at all. You will have no idea what it is. Okay, so that's why I prefer you name all your file names and path in English. Okay, so now let's uh, use a parallel. I purposely select a high performance computer. So this is serial, and this is parallel on your local computer. This is parallel on a how do I say, like a remote computer, and this is parallel on the remote computer and through a file. Usually we just bother with the first one and the second one, and even for most of your personal computers today, you will have like usually you have 4 cores or 8 cores computer, even for laptops. So I would not very suggest you using the serial computational approach. Rather, I suggest you use the parallel computing process. It will be very convenient in both the domain discretization as well as the computational process. Okay, but remember, this number should not exceed your maximum number of cores. Okay, for example, your computer only have 8 cores, and you put a 12 in here. That will make no sense. Okay, and also I strongly don't recommend you to use your computer's full capacity. For example, if you have 8 cores and then you use 8 cores, that will result in insufficient resource for the operating system, and your system may crack down in this way. Okay, the best case scenario is that your system is incredibly slow throughout the computational process, such that you can do nothing, literally nothing at all. And after it finishes its calculation, it may be several minutes or even several days or weeks before you can finally get back the control of your system. Okay, so that's the 2 points about the parallel computing in here. So now I will give it a 16-core parallel due to my high performance computer in here. Okay, so now we have the geometry, continuum, region, stopping criteria, solution history, solution view, and monitor, graphics, summary, and tools. Okay, so basically we have nothing at all. We just open up a new program. So let's click on this file. Oops, sorry. So we have no model at all. It's all empty. Okay, so let's say this file, import surface mesh. Okay, and then open up the folder. Okay, so we have the part well code first. Okay, so this is the create a new part, merge parts by name. Okay, and we can unselect it just to or select it just according to the model feature, depending on how many parts you have. In here we only have 1 part, so this doesn't really matter. Okay, so let's click on confirm, and it is importing the file. Okay, so we have the imported file in here. If you are single clicking this interface and drag your mouse, you may see it moving. Okay, and if you roll the rollers on your mouse, it's zooming in and out. Okay, if you are clicking the right button of your mouse and move it everywhere, it will be a translational movement. Okay, and that's basic movements you can do in Star CCM. Excuse me. What else? So this is a transparent or solid feature, so you can see. Okay, this is the solid feature. This is the transparent feature, so you can see throughout the process. And another thing I would like to mention, every time I want to use that, is that you want to make sure your view is in parallel mode. Okay, so let me give you an example. So this is the view mode. Okay, so this is a aligned view. Okay, so this is a parallel view. So this is like what you learn from the engineering graphics. Okay, from the engineering graphic class. So of course this type of view is preferred. So please do remember to change the view. Okay, and also you see we can have some different type of standard views like this. Okay, and or like this. Okay, so if we are going to and this shows us going to the previous view. Okay, or we can go back and forth. And if I say this view is very good, I can even save the view in here. Okay, save the view in here. So once I messed up the view, I want to go back to my original view, I can restore the view like this. Okay, so that's how you play with the view features in here. Okay, and that's some basic operations. So another thing we would like to confirm is that you see the name is all messed up. So this type of symbolic name is totally not acceptable. So let's save it as this is the well cooked model. Okay, so all we care about is its faces, and now it has only one face. Okay, but remember in our simulation we have different type of boundaries. Okay, we have boundary inlet, we have inlet boundary, we have wall boundary, we have pressure outlet, even for this simple case. Okay, so we need to split these views, and we click on split by patch. Okay, so let's click on here. So I will put this as inlet. So I will say inlet and click on create. Okay, so this part is gone. Okay, and then I need to put a outlet. So this is outlet. Okay, this surface is also gone. And then I have walls, 1, 2, 2. If you click on the control button, you can select multiple surfaces. Okay, so these are wall. Let's say surrounding walls. Okay, so there's only 2 parts left, and if there's only 2 parts left, we can exit in here. So these are faces. We just name them as cylinder walls. Okay, so back in here, any questions so far? After we set up all these surfaces, let's make it transparent. Cylinder wall, inlet, outlet. We just need to categorize them. Okay. Any question yet? I give you 30 seconds to think of this problem.
I have a question, sir.
Yes, go ahead, please.
Is there any reason why we make the inlet closer to to the cylinder wall?
Uh, I'm sorry. Can I beg your pardon?
Yeah. Is there any reason why the inlet wall, why we place the inlet closest to the cylinder wall?
Okay, so this is basically there are so many things I want to show you. So I don't even know what is the most appropriate way. So how do I say? That is a very good question. Let me explain to you theoretically first. Okay, so um, let's have a view. Maybe this is a better view. Oh, I really hate this. So that's why usually when operating this software, yeah, I will select some my favorite rules and save it. Okay, so why do we put the cylinder ahead of the in the front region of the flow of the computational domain? So that's the first and most important issue is that we we extremely care about the wake flow. Okay, so the so you will know later that the flow feature of this cylinder have something like this or something like this, depending on the flow velocity, depending on the incoming flow velocity. Okay, that's one thing. That's the flow feature. Okay, so that's why the wake flow is extremely important. So these are the wake flow region. Okay, so that's why the wake flow region is extremely important. Okay, so uh, that's that's the most important issue right over here. So that's why we need to leave a large area behind or in the downstream direction. So in the upstream direction, which is the direction right in here, okay, um, all we are looking at is the velocity distribution in here. But if we are looking at the pressure distribution, which I will also show you later on, the pressure distribution looks something like this. The pressure contour. Okay, so what will happen in the end if I move the cylinder uh, to towards the downstream region, for example, in the center, is that I will waste some of the areas. For example, I will waste the computational areas in here because they all belongs to uniform flow. This may be an appropriate pen. Okay, this area would be somewhat wasted. It's a waste of my computational resource. Okay, so that's one thing, and the other thing is that if I move this cylinder, say if I want to save my computational resource as much as possible, I move this cylinder forward, but to some extreme value, to some extreme region, and I move my um, say I move my uh, inlet boundary all the way to here. So what will happen is that the physical properties are predefined in the inlet condition. Okay, so this is what we call 数值锁定 in Chinese, and in English it's like a numerical lockdown. Okay, so in this way we force the pressure or velocity in here to be uniform because this is the predefined inlet condition. Okay, so um, In this way, we will not have a uh, or properly developed flow field because we locked some physical properties numerically. Okay, that does not correspond with the actual physical condition. Okay, so that's why we are having this numerical lockdown in here. So that answer your question, Cosmo. We need to select a proper distance, um, no matter it's uh, too upstream or it's too downstream. It both have uh, disadvantages. Okay.
All right, sir.
Okay. Um, so similarly, I want you guys to follow me step by step and conduct. I'm sorry about that. Okay.
So Lashi, this
Yes.
distance is it based on any predefined rule or is just based on experience?
It's just an experience. Unfortunately, it's like train aerodynamics. It's just like a trial and error, like a trial and error thing.
All right. So,
Okay. For train aerodynamics, like you may need to leave about 30 to 50 meters ahead of the high-speed train, depending on the incoming flow velocity, and then you need to leave about 200 to 500 meters in the wake region, in a similar way. Okay. So so this is the so I want to give you guys another 5 minutes to import the surface mesh and then rename all the meshes. Follow my step. Okay. Maybe 10 minutes. Just let me know whenever you guys are finished. Okay.
No, sir. Oh, sir.
Yes.
Uh, I think that I think that is it possible for maybe we can just proceed and then maybe we can do it and submit it as an assignment.
Okay. Okay.
Using the recorded, yeah.
Okay. So based on my experience, unfortunately, give you an assignment will be something I can not do. The reason is because I've been trying this for several classes, and there's always some students claim either they have very bad internet or they have very awful computer. They have very awful computer that they cannot finish up this process.
Yes, sir. And that is exactly the problem now, because
okay.
so many people have either network problems or the software has some issues and etc.
Okay.
So maybe we can proceed,
okay.
and then I will share the recorded file, the recording, and then maybe we can all follow up from there.
Okay, no problem. Excuse me. So then so let's do that at the same time. Let's import surface mesh, and there's a medium well set file. And merge parts by name. Let's unclick them. Okay, so for this part, medium well, we have the cylinder in here, we have the computational domain in here. Let's say that as a computational domain. My computer has a very poor graphic card, so please bear with me. If the background turned into black, there's nothing I can do. So this cylinder. Okay, so this is usually what you will be facing in the actual turn aerodynamic calculation. That your turn model is given to you. You need to build up a rectangular square. That is the rectangular box. That is the easiest way you can do. Okay, and so what we need to do next, first of all, we need to do the same. Okay, the surfaces, and okay, we need to split up the surfaces, but before that, let's see, where was it? So let's use the Boolean option, subtract, okay, and the target object there we go. The Boolean option, subtract, and we have the input parts. I always mess up the order in here, so it can't be either. Let's try. So the input is the computational domain, and the output is the cylinder. Target part is the cylinder. Oops. Or the input is both, and the output is the cylinder. So let's try. And then let's execute the operation. So how's the subtracting here? No good. So let's try re-edit it. Let's say the output is the computational domain. Let's execute. Okay. So Actually, I think we are done with the subtraction. So if we are now looking at the subtraction, you guys can see I have conducted the subtraction. I subtracted the cylinder surface from the computational domain in here. Okay. So then I can rename it into recooked. Oh, by the by, you need to save in time, otherwise you will regret it. So save the file, start tutorial. Okay, so basically this recooked is like the well-cooked model. Okay, it's basically the same. And there's something we haven't done yet. Okay, we need to rename this. Okay, maybe we need to split from here. So actually, that's the accident I was talking about. So this is the outlet. Let's put a C, let's put R as recooked just to differentiate them with the previously defined boundary condition. That's outlet, and that's the inlet. Okay, and that's the wall. Okay, so these are the R surrounding. The R surrounding wall, outlet, inlet, and here maybe at the cylinder. And since we changed the settings in here, we need to re-execute. Okay, if we look at the recooked model, once the exclamation mark is gone, we look at this model. So we can have this faces all inherited in here. Okay, so basically this model and this model is equivalent. It's just depending on which model you are using. Okay, so anyway, let's save a copy. And let's just try to start with the easy one, because we have two equivalent models. It's a little bit too complicated. Let's delete all of this. Delete this operation. Okay, so now we have a model like this. But okay, because this has a much clearer view. Okay, and what do we do next? We have a model already with the surfaces defined in here. Okay, so in the next step, we we need to assign this part into a region, and in here we need to find out that for create a surface for every part, create a boundary for every part surface. That's why we split it. That's why we split the part surface in there. Okay, so after I clicked confirm, there's a region in here. Okay, so the region is given in here. where we have assigned a fluid region. Okay, the fluid region in here. It could be solid region, porous region, or fluid region in here. And then let's build up a new continuum, which is a mesh continuum. Okay, so let's click on the mesh continuum. So, okay, I'm sorry. In the region here, let's change them. So this is in the English, Chinese name. Let's change it to English name. And then here becomes the region. Okay, the wrong name. Region in here. Okay. And then let's select the domain discretization model. Surface reconstruction, and this comes to another knowledge point we've been talking about. Okay, about the mesh generation type, or the grid type. We have Cartesian grid system, we have structured grid system, we have unstructured grid system, and the unstructured system has like a polygon structure, has tetrahedral structure, or other type of structures, you name it. So in here, let's start with some. Let's start with the Cartesian coordinate system, okay? And then let's use the prism layer. The prism layer is used for boundary layer, okay? We are not using this, at least for now. Okay, so the base size is 1 meter. I give you one example. Let's give them a 0.1 centimeter. Okay, and the surface size, the target size, this is the percentage of base. It could be either percentage of base or absolute value. Okay, so the percentage of base, let's say it's a 50. Okay. So this is the thickness of the prism layer, and let's make them a random value, probably 3.33. Okay, so this number of prism layers, let's make it 16. And this is the growth rate. Let's make it 1.2, which is the proper value. And this is the growth rate. This is the surface repair. Okay, this is the surface mesh growth rate. So basically, we've done the domain discretization setup. So in the next step, we can start generating the domain. Okay, first of all, let's generate the surface domain, surface mesh. And you can see the processor is it's already beginning to process the surface mesh. let's just wait a little bit for it to finish. So you can see the current number of faces is 90,000. It's not too bad. Okay, so now we've done with the surface mesh, but we can see nothing in here because we are in geometry window. So if we are going to tool option and going to the views, oh, I'm sorry, not the views, the scenes. Okay, we right click on it, we open up a mesh scene. Okay, so we can see the surface mesh right in here. Okay, so this is the surface mesh. I'm very sorry for my poor resolution computer. So this is the surface mesh which has been generated in here. Okay, and I think I did something wrong. I think I did something very arbitrarily. But let's see. Let's generate a mesh and let's see first, and then let's make some corrections. So first of all, I want to create a new plane, a horizontal cross-sectional surface. If it's not very perfectly horizontal, it's okay. So now we want to displace it in here. Okay, so there's no mesh like at all. Okay, because we only generated the surface mesh. We didn't generate it. We didn't generate the volume mesh yet. Okay. But remember, we just established a reference plane. I want it to be parallel to the horizontal surface. So what we need to do is that we need to find out the definition of this plane. Okay. So okay, derived parts. So you can see the coordinate system in here. Okay, they may not be perfectly perpendicular. Okay, so it's very close but not very perpendicular. So this is -1. This is -1, -0.4, 0.26. And the normal direction is 0, 0, -1. So let's make it a better one. So let's make it 0 and 0 and -1. Okay. So in this way, we can make this plane perfectly vertical. Okay. And then let's generate the volumetric mesh. So it's generating the volumetric mesh now. Let's wait for a little bit for the computer to generate it. I'm sorry. I just made two fatal mistakes. First of all, we don't need surface wrapping. That's where I unclicked it. That's one thing. And second of all, I forgot to click on the parallel discretization scheme. So that's why my domain discretization was incredibly small, incredibly slow just now. And uh, okay, so this volume mesh has completed. So now you guys can see it's very fast. So we have about 15, um, I'm sorry, 590,000 cells, okay? And these many faces, these many vertices. And so what if we don't want these complicated structures? We can open up the grid scene and select the parts we would like to see. Okay, so we are only viewing the surface mesh. I mean, it should show up, but it didn't. I don't know, it's my... Sometimes it's the computer issue. Okay, this may be much better. So I just built up a new mesh scene. So let's select the proper okay. Okay, so there we go. So I need to include the parts this cross-sectional plane need to intersect at. Okay. So see, there's some issue with the collaboration. Okay. I have put a very small surface size. So, which means the surface, uh, the size of the surface mesh needs to be at a very small value, such that it can correspond. It can correspond to the size of the surface mesh. But like I designed in here, okay, the volumetric size is 10 centimeter. I'm sorry, it's 1 centimeter. But the surface size is 5 millimeter. So that's why there's a growth rate in here. Okay. So, and also there's something very ugly in here. For example, the wall, the inlet and outlet, they are very, very, how do I say? They don't need this type of fine grids because they are far from the flow region we are investigating. So there's something we didn't set properly. So this is the cylinder wall. There's nothing we need to adapt. Besides this, how do I say, the generalized rule, we can apply specific rules for here. So in here, we apply the wall boundary condition, which is not. So we can change the boundary condition from wall. This is the inlet, okay? So we need to apply it as a velocity inlet, okay? And then, so this is a velocity inlet. Alrighty. And similarly in here, we need to set it as the pressure outlet in here for the exit, okay? And for here, they are the surrounding walls, mesh conditions. So there's a custom surface size. We can customize its surface size in here. Okay, so the surface size, let's set it to a relatively large base size, 0.01 meter. I think this might be acceptable, but let's give it a 10 centimeter. Let's give it a 5 centimeter. $800, maybe too much. So what we have 800 in here. We have 2,000 in here. Okay, so I wouldn't say that. I wouldn't have a too large value. Maybe 250 is a better choice. Okay, so surrounding walls in here. And if we go to the mesh values, the physical condition, the boundary, okay, that's one thing. That's for the domain discretization. Let's see what's going to happen once we adapted the setting. Okay. Okay, still. we have increased or we have decreased the number of faces, but for the inlet and outlet, we forgot to adapt the settings. So we can see the values are much smaller in here. And let's set a base value, which is a smaller one, which is 0.0025 meter. Okay, and so the 250 outlet mesh value, surface size 250. Oops. Sorry, what I mean is 25. So it may be, let's see what's 100. Okay, so maybe this is 1000, and this is 1000. And also custom surface size, check this for the inlet 1000. Okay, and then let's see what it looks like now. Okay, so basically this is what the mesh looks like right now. Okay, at least we have an acceptable mesh so far. Okay, so that's without the boundary layers. Let's just save it first. Okay, and then in the next step, let's select the physical model. Okay. Then here, there's the steady state model and the unsteady state model. Okay. And so we have a steady state, we have a gas over here. Okay, and we have separated flow and coupled flow. Let's select the coupled flow or separated flow. It's just a matter of efficiency and accuracy. We don't explain too much in here. Let's say it's an ideal gas. It's a polynomial gas density. It's a constant gas. Okay, so uh, let's put it as a constant gas, and let's put it as this is the turbulent flow, this is the in viscous flow, this is viscous rhythmy, this is laminar flow, in viscous flow, and turbulence flow. Okay, so we can select the turbulence flow in here, and then there's a model we are very familiar with. So this is star CTM. It has many K epsilon turbulence model, K omega turbulence model, Reynolds stress turbulence model, SA turbulence model, things like that. So we can select, we can from low Reynolds number Ragami, we can just select K epsilon model. Okay, and for the rest of these models, they can be either selected or unselected. So let's just ignore them so far. It's good enough for the calculation. Okay, and so there is air in here, and the properties of air is shown in here with the dynamic viscosity and its density as constant. Okay, so these are the values in here. So this is the inlet condition. We forgot to apply its velocity. Okay, its velocity now is 1 meter per second. Let's give it a faster flow rate, like 10 meters per second. Okay, so we have discretized the model and selected the appropriate numerical solver. So there are several other things I can show you. What do we have? Yeah, the monitor right here. Our report. Okay. So what do we care about? Let's take one thing as an example. We care about the force. Okay, the forces and the load on the surface of the cylinder. So let's take a new report. There are different type of values, like volume integral forces, moments, things like that, coefficients, things like that. I strongly don't recommend you to use the coefficients because there are some very hard, there are some tricky values such as the characteristic length and characteristic surface area is very difficult to obtain. So in this way, let's just derive the force, okay? And then let's derive the force is number of newtons, and on what type of parts we are worried about. We are worried about the forces applied on the cylinder wall. Okay, so that's why both the cylinder wall and the surrounding wall are the wall structures, but in the surface definition we separated them. It's not because it's redundant, it's just because it's necessary. Otherwise, in the monitor system, it will be impossible for you to monitor the forces, okay, or forces sorely on the cylinder. And also, you can even subdivide these first forces of the cylinder into some subregions. and you can derive the forces applied on the subregions of the cylinders one by one. Okay, so click on OK. You have a force. So let's say the force on cylinder. Okay, so that's a force. And also, let's put a new probe in here. Okay, so this probe is one of my most favorite features in Star CCM. Okay, so if you are looking at this probe, you can put it in anywhere you want, and it can visualize your probe. So what do I do? You can either put the coordinate systems of your probe manually. So now it's 0.26. You can put it into 1. Okay, in height. So you know it's changed already, and let's go back to 0.26. That's because this is where it's originally heads. So on the y direction, I suppose this is a y. Oh, in x direction, you can move it either upstream or downstream, like -1, okay, or 1, okay. You can move it up and down, or you can single click on this probe and drag it everywhere. You can see the coordinate is changing, but your mouse is never going to be as accurate as the numerical data. Okay, so let's put it as 0, 0 as what it is. Okay, and let's create. I created 2 points. We can create many points based on our definition, based on the specified coordinate location. Okay, so let's say this is the origin probe. So what can we do about it? In the report section, usually we use this maximum value. So let's measure its velocity, and let's use this origin probe. So it measures the velocity change throughout the process. Okay, so also I can run a new maximum value. Let's say pressure. Oh, I'm sorry. In the velocity, I forgot to define its velocity. So we have the velocity. We have either the velocity in I, J, K, or I, which means x and y direction. We can use the velocity magnitude. Now let's select the velocity magnitude. And this pressure, we can measure the pressure in here. Okay, which is the pressure. This pressure is the gauge pressure. Okay, and let's select the parts as the probing point. So what can we do on the next? So we can create monitor and drawing according to the report. So this is what we do, and do the same for the rest too. Pressure and velocity. Okay, so now basically we have finished up the domain discretization, the solver selection, as well as the initial condition, boundary condition setup, and also we have set up some probe and monitoring scheme. For example, like the forces in here. Okay, so what do we have? What's next is the stopping criteria right in here. Okay, it could be either using maximum steps or using a stop file. Okay, let's don't use the stop file. Let's use the maximum steps. Okay, and click on the maximum step. Let's give it a 10,000. Okay, and so this is the basically pretty much what we need to do. I think there's something I didn't set up, but it's kind of like an automatic option, which is the initial condition. Okay, the initial condition, use the continuum value. Okay, let's say the initial condition is 10. I think I may set up the flow in the x direction erroneously. Let's double check it. Inlet condition, 10 meters per second. Okay, let's give it a look. We will see what happens, because it there's something unsmart about the star CCM. We'll have to look at it later. So initialize. Okay, it has done initializing. Now this is run the calculation step by step. This is run the calculation all together, and let's run the calculation and see what's going on in here. So this shows your iteration step, and this shows you the convergence status. It will gradually go down, okay? Gradually, but definitely go down into some certain level, and this is what we call the convergence level. And in the same time, you can see the monitored velocity and pressure, as well as the forces on cylinder. Okay. So remember, we are investigating the steady state problem. Whenever you see a regular fluctuating pattern, that means that the flow field has developed into a steady state. Okay. So let's wait for a little bit, and during the calculation time, let's wait till like 4 o'clock. Let's take a break, and after the calculation's done, let's have a brief discussion about the results. Okay. And in the meanwhile, if you are having any questions, please feel free to ask at 4 o'clock after we get back. Thank you. Okay, everyone. Excuse me. So let's let me ask you, do you have any questions so far regarding any of the process about the domain discretization, the solution process, things like that? Any questions so far? I'll give you 1 minute to think of this, to answer this. If not, we will proceed. Okay, so we are having limited time in class, so I'm not going to waste further time. Okay, so we are not going to waste further time for the simulation to accomplish. So, and that leads us to one final question. What is the proper iteration steps? Okay, so all you hear from the CFD expert is say like try like 5,000, 10,000, or 20, 30, 50,000. Okay, so what we are looking at actually is the continuity curve right here. Okay, so I think this graph is very, very beautiful. Actually, so beautiful, I need to take a screenshot on myself. Please excuse me for a sec. It's a very valuable picture. And if we look at the velocity monitor, pressure monitor, force monitor, so what we can observe, still it has the same rule. You can move on your rollers on the mouth, so you can see the force distribution. Okay, so we can see the force is barely moving. It's getting very, very stable. The pressure is getting stable, and the velocity is getting stable. Okay, so that's for, and also the residues are getting much, much smaller. Usually for fluid dynamics, if we can get a convergence curve below the level of 10 to the order of -3, which is 0.001, we usually think it's already at a very good convergence level. For train aerodynamical study, unlike the flow around the cylinder, which is a very, very simple case, we might have a extremely complicated, geometry, and very, very poorly, very, very poor quality mesh. So that will all lead to the decrease of convergence level. So let's just suppose that this convergence curve will just remain flat, which it will probably remain flat as time goes by. But but we are not waiting that longer. So let's just assume it's going to be flat from here after. Okay, so and what we do next? For example, if we want to get the pressure data, if we want to get the velocity data on the prop point, we can just derive these points, and let's see. So all this report, we can subtract this data. Okay, we can subtract this data and then save them and export them. Okay, and conduct a average or something. Okay, so um, so this is pretty much how we deal with the calculation. Uh, let's start from here. Okay, let's save it. Once we are done the calculation, in the next step, what we need to do is the post-processing. So we can, like I said, we can derive numerically the force data, the velocity data. Okay, the x-axis is the number of iteration, the y-axis is its value. Okay, same as the pressure, except for the velocity value becomes the pressure value, and this is the forces on the cylinder. So what we can do, like I mentioned already, we can transform these forces into coefficients. Okay, like drag coefficients. So that is really what we do for the post processing. Okay, another thing I would like to mention is that besides that, what we are usually observing is the how do I say, the contours given by the software, such as the velocity contour, the like the velocity contour and the pressure contour. So let's see where that is. Okay, there we go. So first of all, the contour must be in the 2D surface. Okay, so let's select the surface we defined right here. Okay, and did we change? Yeah. Okay, there we go. Excuse me. Excuse me. So first of all, we select the cross-sectional plane we predefined, and then let's select the function, which is the pressure or the velocity. Excuse me. Velocity. Same. Let's choose the velocity magnitude. Okay. So you guys see the mosaic in here. Okay. This mosaic is reasonable because we just have this mosaic points. There are something we could do about these mosaic points. So first of all, where's that? Yeah, let's increase the number of points. 60.1. Oops. Okay, guys, if we look at the grid system, in here, okay, we can find out that this grid system actually is best because the grid has a very poor resolution. Okay, so this is just a simple demonstration of what the flow field should be look like about the domain discretization, um, the domain discretization, the selection of numerical solver, the application of boundary conditions and initial conditions. Um, Now let's make it a more sophisticated and more reasonable system. Okay, so let's go back to the grid system. So what we can do, we found out that the flow in here is very delicate, so that we need to have some very fine grid systems. So what we can do, first of all, um, we go to the grid section, and then let's take a look at the surface size. Okay, since we already specified the sizes of the surrounding walls, we can specify a much smaller surface size of the grid. Okay, so we can say the target size is, how about 5? Okay, so in this way the surface size is much smaller, or I think 10 will be small enough. Okay, so the surface size is one thing, and another thing is that we want a higher resolution, especially in the core flow area. So so I'm sorry, before that, let's add another model, which is the prism layer. Okay, so this prism layer corresponds to the large velocity gradient on the peripheral region of the cylinders. Okay, so then we have the thickness of prism layers. So this thickness of prism layers is all correspond to a y plus value calculation. So it's like what Eze just asked in the beginning of the class. It's all based on trial and error. Okay, so in here, let's just use a arbitrary number. So the thickness of the prism layer, let's say, I think it should be around 3 millimeters based on my experience. Okay, let's make it 4 millimeters. Sorry, that's not good enough. Not too much. Okay, 4 millimeters it is. Okay, and then there's a growth rate of the boundary layer. Let's make it a 1.05. And there's a number of prism layers. That is something you need to calculate. Okay, so what I usually do is I open up an Excel file. So I'm doing the calculation at the same window. So from 1 to 16, okay, we have the growth rate of like 1.05. Okay, let's suppose the first layer thickness of the first prism layer's thickness is about 0.05 millimeter. Okay, and then I let it, the second layer would equal to the first layer times 1.05. Okay, and all the way down to layer 16. And then I sum up all the numbers together. See what do they get. So it's 1.18. So the first layer may be not large enough. So what about 0.1, 2.36? Still, let's try 0.2, 4.7, 1.18, 4.25, close enough. What about 1.1, 0.16, 0.17? Okay, through trial and error, in Excel, we set this thickness to be actually it's 4.02, but it's okay. And the growth rate is 1.05. The layer is 16. Okay, so okay, and that's for the prism layers. But there's another thing we need to pay attention to, okay, which is that in the boundary condition, we have the we don't need the boundary layers in the inlet or outlet or the surrounding walls because they don't have large velocity gradient over there. So we want to uh, forbidden the application of boundary layer in the cylinder wall, the inlet, and as well as the outlet. Right? So we don't want the boundary layers in here, 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 and here. We just want the boundary layers on the cylinders. Okay? So inlet, oh, I'm sorry, cylinder wall, we need to use the boundary layer. And the mesh values, outlet. Okay, so now let's try. Let's save as another file. And now let's try build up the mesh. Global target size must be greater than the minimum size. What was the question? Must be greater than the minimum size. I'm a little confused. Must be somewhere I did wrong, but Sorry, guys. Please give me a few sec. I need to figure out what is going on. I just got stuck all of a sudden for some reason. Probably just some problem with the prism layer. Let me think of it. And in the meantime, if you have suggestions, you can feel free to speak. It will be very appreciated.
Oh, sorry, Laura, what's the particular problem?
There's the warning of error in here. I've never seen this before, so I need to think of a reason. I think we found out the problem. Probably it's in here. So let's try. Okay, sorry. Back to square one.
So I think it has to do with the meshing model.
Yes, I think it definitely has something to do with the boundary layer. Okay. I think I found out the problem is the surface size of the cylinder shouldn't be smaller than size of the prism layer. So that is the reason. Okay. So I have adapted the surface size of the that is because the error I was having is because the mismatch between the surface size of the cylinder and the size of the prism layer, which is the boundary layer. Okay, so let's wait for a little bit, and we will see boundary layers generated on the peripheral area. Okay, guys. So now we have the boundary layers. Okay, looks something like this, but there's something wrong with it because it did not increase linearly. So yeah, I think it should be looked something like this. If we should change the option, that's one way to apply the boundary layer given an acceptable low flow rate. But this boundary layer, according to the theory, it should be very, very thin on the first boundary layer and gradually increase as the boundary layer is getting further away from the surface of the physical object. Okay, think you guys can pretty much see the trend because our increasing rate is 1.05. It's very small, and that's another requirement. So just so you know, there's a ruler function in here, so we can measure the distance. So the first boundary layer is around 0.0018 meter. Okay, and we can take another measurement, which is from here, the last boundary layer. Oops. Oh, I'm sorry, wrong button. 0.0034. Okay, this corresponds with the predefined boundary layer increase rate we just mentioned. Okay, so this is the addition. This is the setting for boundary layers right in here. Okay, so that's one important thing I would like to mention. The other important thing, we have seen that the result now it doesn't look like this because we have finer boundary layer. However, the grid resolution in here is very, very poor. So what do? We want to apply local refinements in here. So what do we apply local refinements? There's the body shape in here. We apply a new shape. So here is what I enjoy the most. Okay. About the shape of the local refinement. So basically we can refer to the local refinements given by the system and then make corresponding improvements. Okay, so the x is negative 0.36 to negative 0.63 to negative 0.37. So the middle point would be somewhere in negative 0.45. So let's make it this, and okay, oops. Maybe too small, so okay, and oops, I hate to play with the coordinate transformations. Oh my god. What did I do? Okay, yep, I think that's pretty much it. For the y direction, let's make it a better looking number. How about negative 0.14? Okay, and similarly, positive 0.1. Okay, so remember this is the 3D simulation. Okay, it need to have spatial distance. So the thickness is 500 meters. We can make it all the way through to make it the bottom level would be negative 500, and this, and give it a positive 500. Okay, I'm sorry, it's too much. It's not 500 meter. It's negative 0.5 meter and positive 0.5 meter. Okay. And now maybe not enough. Let's make it as tall as possible. So that's 1, and that's 1. So in this way, we can make sure that this region totally covers the cylindrical region for refinement. Okay, so that's for 1. And then we can do the same, okay, but with a broader range. So let's make it negative 0.7, maybe too much. 7, I mean. And then this is maybe .4. See where it goes. Okay, and then we expand it a little bit to negative 2, 0.2. Not bad, maybe not good enough. To 5, okay, pretty much, and positive to 5. Okay, and this may not be far enough. Maybe not. Okay, so let's click on great. So we have 2 block regions, 1, 2. So this is the fine region. This is the medium fine region. Oops. I don't know what's happening. So this is fine region. This is medium fine region. Okay. And what are we doing? Going to the mesh section. Okay. Apply volumetric control. Okay. So what is the target size? So the target size is 0.025, and the surface size was what? inlet 0.05 meters, 50 millimeters. Okay, so 50 from 50 and make it 40, 20, 10, maybe 10, 5, maybe 5, 10. Okay, so where was it? So the part, we need to select the part and select the shape. Let's start with the fine. Okay, and the fine region, and let's set up the mesh condition. Select the isotropic size, custom size, relative size. So what the spatial resolution would be? I would say 1 millimeter. Oops. I don't want relative base. I just want the absolute value. Maybe 1 millimeter would be a better choice. Okay, that's for the fine region. And what about the rest? So let me think. $50 millimeter. Much. Let's give it a 5 millimeter. So that's for one, and let's use another one. Mesh condition. Mesh condition. The other was 1. Excuse me. The other was 1, and this one, let's give it I think 4 may be acceptable. Sorry, not 4 meters, 0.004 millimeter. Okay, so we have applied boundary layer, and we have applied local refinements, and now let's generate a mesh and see what it looks like now. Okay, this may take a little bit longer, so it's breaking time anyway. So let's take a 10 minutes break and get back until the mesh generation has finished. Okay, let's get back at 10 minutes later. For those of you who wasn't aware of what happened, I'm sincerely sorry because the software collapsed. It just happens every now and then, and I forgot to save the operation process, so I need to restart. So let me open up the resource monitor. It's not too bad. So this usually happens when you are having a very you are operating in the system for a long time. It just crashes every now and then for whatever reason it could be. So you just have to deal with it. Oh my god. I mean, it just collapsed again. Excuse me. Let's do this. I'll redo the setting and let it run domain discretization process on its own. And in the meantime, I'll do something else. Thank God I saved it. Okay, so now this is the mesh scene, and let's see if I set it up correctly. Volumetric control, volume control fine, volume control medium, okay, medium fine, fine, medium fine. So this is fine. Value 1 millimeter, 4 millimeter. Okay, looks about right. So let's forget about the the new generation first. Let's firstly export. So export to inside code. So I'm only exporting the mesh, okay, and I'm saving it in the folder. So okay, save it. So now let's redo the mesh. I will just leave it as what it is for here. So what I want to show you is how to use the computational processing ANSYS Fluent. Okay, so Let's switch the screen sharing window. Okay. So this is a launcher. We have a 3D model. Okay. And we need to have the path file. So let me locate the path file. It's right over here. Okay. Make sure it's usable. And this is the installation root path. And let's use this course. Okay. And parallel computing, double precision. It doesn't. We doesn't need that high precision. Just since it's just a demonstration processing here. And yep. So this is basically how do you start up the launching mode of ANSYS Fluent. Okay, so the launching mode, the launching window disappears right after the formal Fluent window. Okay, so I think you guys now can see the Fluent interface now. So actually, the Fluent was purchased by ANSYS system years ago. So the Fluent software itself is not capable of processing, conducting the domain discretization. However, there's another software in ANSYS Fluent system, which as ANSYS SCEM. It is capable of generating the meshes. Actually, it's more capable. Actually, it's no worse than Star CCM. Every software has its own advantages. The ANSYS SEM is also a very complicated software, but I'm not very familiar with that domain discretization tool, so I will just skip that session. Anyway, so just say we've already we are already having the domain discretization files. Okay, so you see you can also import from Abacus. We can import from Insight. Insight right here. Okay, so click on OK. So you go into importing. Take for the system to respond. Still reading. Takes a while. Yeah, the star CCM file collapsed again, and I think that's mainly because the size was too small. The excuse me, the element size I set is too small. It's beyond the capability of this computer. It just ran out of memory. So I will try some larger number. Maybe we can switch back. Please excuse me for a sec. Volumetric control. Okay, we've done the import in the ANSYS Fluent section. So here is also a two-type of window, but I will show you later. First of all, a lot of beginners for ANSYS Fluent will begin wondering, I have done the import, where the hell is my model? Okay, so to show your model, first of all, you need to click on display, okay, and select the features you would like to display, and then click on the display in here. Okay, so there's our model right here. Okay, so this is the ANSYS Fluent software. Okay, we have the boundary layers already. Okay, and what else? You can click on scale, so you can know the distance of your model. Okay, an x direction, in x direction is -1 to 1, in y direction is -0.4 to +0.4. In z direction is basically 0 to 0.5. Okay, so this is more convenient than star CCM. And this is the feature view. Okay, and what is this? For example, if you accidentally moved your model to somewhere you have no idea where it is. Okay, so the roller keeps moving in and out, and if you click on the control button and click on your right mouse, you can move this picture, you can move your model everywhere. Okay, so in some scenario you have no idea where your model is, just click on this button, fit window, and it will go right back to you. Okay, so and the other very inconvenient feature about ANSYS Fluent is that it doesn't have automatic saving option. So what you need to do is you need to click on File and Write and Case and write your own case. Okay, so yeah, Fluent. Okay, so what we need to do in Fluent, sorry, something, I need to deal with the Star CCM software for a little bit, but let's switch to this window. Be right back. Okay, so sorry about that. So we have, these are the solver options. This is something different from the star CCM. So the solver option displays some parts of the solver options display right here. Some of the solver options we need to select manually. So I'll walk you through one by one. So this interface is in some ways more complicated than star CCM, but in other way it's more how do I say, successive than star CCM. So the pressure based and density based correspond to the segregated flow and the coupled flow in star CCM. And the velocity formulation has absolute or relative velocity formulation. We usually choose absolute. I will, because it's a little bit complicated theory, I will not explain too much in here. For the steady and transient option, we also can select that in star CCM in the numerical solver option. And this is the gravity button. You can select whether you want to open up the influence of consider the influence of gravity or not. In star CCM, you can still do the same. Okay. So now that you have your model, geometry model, and as well along with domain discretization. So what you actually need to do in the next step is to select the model. So you click on the edit viscous laminar. So we have the inviscid model, SA model, K epsilon model, K omega model, transition KL omega model, and transition SST model, Reynolds stress model. So that's why I mentioned already. Okay, there is LES model and DES model. Actually, the star system also has DES and LAS model, but it's based on LES or K omega LES or K epsilon DES, which you can see in here. Okay, so still let's use the K epsilon model, same as the settings in star CCM. Okay, so we can have, there are submodels about standard K epsilon model, RNG K epsilon model, realizable K epsilon model. So that's why I say the ANSYS Fluent is a much more complicated software than star CCM, and there are different Wolf functions. But according to these functions are very well known Wolf functions in the academic world. However, for star CCM, it only has its own functions, which is known as the double Y plus Wolf function, and each of the Wolf function has its advantage in some specified area. I will not use too much time explaining it. Let's proceed with the K epsilon model. So that's for one thing, and the energy equation basically means whether if you want to consider the compressibility of air or not. Okay, since we are using the constant density setting, we don't need to worry about the compressibility of air. So that's why we don't use the energy model in here. Okay, and the species model, we don't care too much. The discrete phase model is when we use the particles flow in the air, we can use that. Model, but now it's not our main topic today. Okay, so we have the material type as fluid and the fluid material type as air with a constant density and constant viscosity. So if we want to change the value, we just need to change the value in here and click on change or create. Okay, so we don't have, although we don't have any solid regions in here, it still has provided the region for solid region. Okay, excuse me. The star CCM software collapsed again all over. I need to find out what is going on with it. Sorry, just want you to have the taste of the local refinement. I don't know what is going on with it. Anyway, so we have the cell lumen region in here, and we have already set it as fluid. Okay. So now the boundary condition is what we've been predefined the boundary at the domain discretization process. Okay, so this is a cylinder wall boundary. I'm sorry, I don't know why it just wouldn't go further to the left. It's really annoying, but try to deal with it. So this is a cylinder wall boundary. Let's right click on it and click on edit. So this is a stationary wall, moving wall, and a sleeping wall, no sleeping wall. Okay, and so we have an inlet boundary condition. It's also set it as wall. Okay, if you can see in here. So what we do, we right click on it and click on the type and click on velocity inlet. So the window will automatically pop up. So what we do, we can apply the velocity, which is 10 meters per second. Either we can have this magnitude normal pool boundary, or we can use the component, which is x and y and z velocity. Okay, so now let's use the easier version. Let's make a 10 and normal to boundary. Okay. Okay, so it's 10 meters per second. Okay, and then for the outlet is pressure outlet. So we need to have the pressure outlet right in here. And sorry, right click on it, select type, and pressure outlet. So the window will directly pop up. We set up the gauge pressure to 0 pascals. Everything is basically predefined already, so we just need to click on the surrounding wall, which is the same with the cylinder wall. Okay, so for the reference values, we do not need to worry too much about it. So the solution method, we have simple C, piezo coupled. These are all very well-known solution methods in computational fluid dynamic history and theory. And for the solution process, do you have any question? Yeah, I think Cosmo accidentally opened up his mic. Let me mute it. No, but not. Okay, there we go. So the solution method and controls are all shown in here. Okay. This is the monitor point. Besides the residues, we can plant seeds like what we did in Star CCM, but I'm not going to waste too much time talking about it because we've talked about the similar features already. And similarly, in Star CCM, we have initialization. So we have hybrid or initialized or standard initialization. If you want to save your time, you can just use your hybrid initialize scheme. So the system will automatically initialize. Okay, so see the system is conducting initialization on itself. So just for wait a little bit, there's only 10 steps. Okay, so now it shows the hybrid initialization is done. So what we are doing in the next step is double click on the run calculation menu and put on the number of iterations. For example, let's give it a 10,000, like what we did in the start CCM, and the reporting interval during simulation, we set it as 1, which has for every step report 1 data. So and in this way, we finish up the setup in ANSYS Fluent. So we can now click on the calculate button and see the convergence curve in the ANSYS Fluent. Okay, see the iteration and the residue menu has shown up in here. So similarly to what we did with Star CCM, we can wait for it to finish up the iteration process. Let's give it another 5 minutes and see how far it can go and compare the convergence process with Star CCM. And in the meantime, you have any question, you can feel free to ask. Okay. I'm sorry that my Star CCM software keeps collapsing. Uh, Unfortunately, I may not be able to give you the results for the Star CCM mesh generation with local refinement at this time. But during next time, I will show you the local refinement results. Okay, so sorry about the all of the software crashing issue on Star CCM, and also we don't have enough time to wait for the answers fluent simulation to finish. So we will see the answers. We will compare the answers along uh, in between the answers fluent and the Star CCM in our next class. Okay, I'll see you guys next week.